And now for problem 23. This was my favorite one on the test, actually. So points A, point A at 6, 13, and B at 12, 11 lie on a circle omega in the plane. Suppose that the tangent lines to omega A and B intersect at a point on the x-axis. What is the area of omega? So if we sketch out these 2 points, then, okay, so we have points A and B, and we want to find, basically we're trying to find some omega. We can restate this as trying to find a circle omega such that the tangent lines to omega A and B intersect at a point on the x-axis. And so in general, the tangent lines will, the main thing that we are going to use is the fact that for any circle, if you draw tangents at like A, for any circle, if you draw the tangents at A and the tangent at B, and they intersect at point T, TA is equal to TB. And this is actually enough for us to basically immediately know where the tangent lines to omega A and B intersect. It's the point T here, so that TA is equal to TB, and T is on the x-axis. And once we get this, we can draw in the line perpendicular to both of these tangents, and this gives us the center of omega. Okay. But how do we find T? So if we let T be equal to the point x comma 0, then basically we just want the condition that TA is equal to TB. So TA squared is equal to TB squared. So 6 minus x squared plus 13 squared equals 12 minus x squared plus 11 squared. So subtracting 11 squared from both sides and doing difference of squares. We get this. And then canceling, this gives us that 18 minus 2x is equal to 8. So x equals 5. So the point T is, we can write this more simply now. T is the 0.50. And so now all we have to do is find like the radius of omega, and then we'll get the area. And so actually the way I stated it earlier is not actually how I want to do it. The way I stated it before was that we would then consider the line tangent to TB at B, utilizing the fact that tangent lines are like that OB is perpendicular to BT. But instead, we can do this with the most common trick by far in AMC geometry, which is similar triangles. So if you let that be the midpoint M, then this line is, this is a perpendicular. Yeah, so AB is perpendicular to OT by symmetry, basically. Yeah. And then we have, nicely enough, that triangle TMB is similar to triangle triangle TMB is similar to triangle TBO. This is because they both have the same vertex angle at angle T, and then they both have, TMB has a right angle at M, and TBO has a right angle at B. And utilizing this fact, notice that, so first notice that M is equal to the point 9, 12. So TM is equal to square root of 4 squared plus 12 squared, which equals square root of 160. And TB is equal to square root of 7 squared plus 11 squared, which equals square root of 170. And MB is equal to square root of 3 squared plus 1 squared, which equals to root 10. And as a quick sanity check, TM squared plus MB squared is equal to 2EB squared. And so using the similarity condition, we have that TM to MB is equal to TB to BO. So BO is then equal to MB over TM times TB through a little bit of equals through cross multiplying and then dividing MB times TB over TM, which equals root 10 times root 170 over root 160. We can cancel that. And so now the area of omega is just pi times the radius squared, which equals pi times 170 over 16. And canceling a factor of 2 from the top and bottom, this gives us 85 pi over 8, which is answer choice C. Et voila.